All right. So hello. Welcome to ASICS seminar series. Today we are excited to have our speaker, Dr. Munchak, joining us from NASA Gather. And I'm John, the seminar coordinator. I will be the moderator with Miss Kathy Medney. And Kathy is our communication specialist. Just so you know, then the seminar is being recorded and will be published in our YouTube channel. Please feel free to ask questions through chat or raise your virtual hand, and we will unmute you. And let me give a brief introduction about our speaker. So Dr. Joe Munchak is a research meteorologist and NASA Gather. He completed his BS and MS in meteorology at Penn State University in 2006. And his PhD in atmospheric science at Colorado State University in 2010. He was a research associate and assistant research scientist here at ASIC from 2010 to 2015, and then he took his current position at NASA Gather. So Dr. Munchak's main research interests are in the integration of passive and active microwave measurements to improve retrievals of clouds and precipitation. This work has many avenues which Dr. Munchak has engaged in current and past research investigations, including the development of three-dimensional inverse methods, optimal parameterization of rain and snow particle size distribution, and development of clear air retrievals for precipitation detection, and surface characterization for active and passive sensors. Dr. Munchak is currently a PI on the NASA Precipitation Measurement Mission Science team, and he serves as an associate editor for the journal Atmospheric Measurement Techniques. It's welcome speaker, and I will hand this over to Dr. Munchak. So Dr. Munchak, please proceed.
Thank you, John, for that introduction. So as John mentioned, one of my recent roles has been the GPM ground validation deputy project scientist. And this work really encompasses a lot of areas of research that I think the GPM ground validation program has really taken some great measurements to enable and advance research in. And primarily what I'm going to be speaking about today is the ice phase of clouds and precipitation and how we measure them with remote sensing and what some measurements can be made to better characterize those. Okay, so just to give an outline of the overall presentation, of course, the ice, as we know, is very important to precipitation, both from the formation in a process standpoint, but also from the remote sensing standpoint. And I'll share some examples of why that's the case. Our modeling of ice, especially for radar and passive microwave radiometer, has really evolved over the past couple of decades, and especially in the most recent decade. And so I'm going to show a little bit of that history and kind of where we're at now with regards to the radiative transfer modeling side and how well we can simulate those scattering properties. And then particularly with the microwave and dual polarization radars. And then I'm going to go into the field experiment portion. A lot of these are, again, GPM ground validation. The main one that I'm going to focus on is this ICE POP 2018 field campaign that was held in South Korea during the recent Winter Olympics there. It was really a great opportunity to get some measurements of snow. And the instrument that I'm going to focus on mainly is the NASA D3R radar, which is a dual-polarized, dual-frequency Doppler radar. But I'm also going to talk about the ongoing impacts, EVS-3 mission. So that's another airborne field campaign based on the east coast of the United States to investigate winter storms. And last year was the first year of measurements for that. And we're planning to go forward with operations again this year, despite the restrictions. And hopefully we'll have some good storms to sample, and we'll do that the following winter as well. So that's a 3-year mission with another couple of years of analysis that have been funded by NASA headquarters. And And I'll finish by talking about a few future instruments that should improve our measurements of the ice phase of clouds and precipitation and missions that those might be involved with. Okay, so it goes without saying that ice is very important in the precipitation process, but I think it's only been recent that we've had the type of observations to really quantify this on a global scale. And so just this past year, there was a paper by Andy Heimsfield in the Journal of Atmospheric Science where he took a lot of spaceborne observations from GPM and CloudSat to kind of investigate what is the fraction of precipitation that falls as snow at the ground, what precipitation originates, what fraction originates in the ice phase higher up, and what fraction still may have some contribution from warm rain, but still has some contribution from cold rain as well. And it's quite fascinating. So for those first two, the percent of precipitation that originates as ice, whether it falls ultimately as ice or snow, is 63%. Then a further 15% is growth of raindrops below the melting layer. That probably wouldn't have happened if you hadn't had this initial precipitation originating from aloft. So that's nearly 80% of precipitation globally that's influenced by the ice phase in some way. And then the remaining part is of course, sort of the purely warm rain. And that's our best estimate for measurements that we have right now. Like I said, mostly CloudSat and GPM and products derived from those. So that's quite significant, obviously. And of course, improving our knowledge of these processes will go a long way to improving predictions and understanding both on the weather timescales and the small mesoscale models all the way up to the global climate simulations. Okay, and the physics is not necessarily straightforward. And one of the areas of research that GPM ground validation is also involved with is this is in a collaboration with the Department of Energy ARM program, is looking at these aerosol impacts on precipitation, and particularly how it influences the ice phase by affecting kind of the originating population of cloud droplets that are lofted into the ice phase. And so, of course, there's a lot of theory surrounding this. The idea is that as you increase your aerosol concentration in CCN, you'll have a population of cloud droplets that's greater in number, but smaller in size. And so they'll be less likely to coalesce into rain with the warm rain process. And that provides for pathway for more ice to nucleate once they're lofted into the colder regions of the cloud. And that can affect cloud lifetime, making an opacity by making the clouds more optically thick and last longer. And there's all sorts of feedbacks that would then arise from that. So these are important processes to measure from a variety of standpoints. And so I just wanted to illustrate a couple of reasons why that's the case. And so it's really important to know the microphysics and measure them, not just try to get a rain rate out of it. Now, on the remote sensing side, as many of you know, I've been involved with the GPM mission for quite some time now. And GPM is one of our best tools for measuring precipitation from space. And the main overarching purpose of it is to unify the constellation of passive microwave radiometers. So there's about a dozen of these in orbit currently. There's always members going in and out of the constellation. But one of the primary ways that we measure precipitation, especially over land, is by detecting the ice phase. And this is just an illustration here. I have some images from GMI over Italy. And this is on the top, the 18.7 gigahertz channel, and on the bottom, the 89 gigahertz channel. And I just wanted to look at the signature of precipitation. So you can see the land-ocean contrast quite clearly at 18.7. But over the water, you can also see these darker features, and those are just warmer brightness temperatures associated with rain. That's just the liquid signal emitting rain. And you can see that quite clearly over the water, but over land, it just disappears. It doesn't necessarily mean it's not there. It's just that there's no way to distinguish that signal from the emission from the land surface. However, when you look at the 89 gigahertz over that same area, near the southern half of Italy, you can see that same line of rain over the ocean, then extending over land. And this is actually a line of thunderstorms that had some hail associated with it, as I recall. And so that signature shows up quite clearly over land and water. It's pretty seamless. You can't even, if you look at the cloud area, you really can't tell the coastal transition. And so it's the ice signal that's producing this at the higher frequencies, and it's quite important to measuring precipitation. And I just want to highlight a recent paper by Yale Yu, who I work with and is an ESIC research scientist, that he published in the Journal of Hydrometeorology, where he actually evaluated the skill of all the members of the GPM constellation, and found that over ocean, the best performing sensor is Anther 2, which has these lower frequency channels and a higher resolution. So as you might expect, it performs pretty well. But all the other sensors probably perform equally well over water. But over land, that skill advantage of Anther 2 goes away, and all of the sensors perform equally well, whether they have those lower frequency channels or not. And Sapphire actually only has high frequency scattering channels, and it still does just as well as the other sensors. So this really shows how important that ice signal is. It's really the only signal we have over land with respect to precipitation. So when we launched GPM, GMI had that 166 gigahertz channel, which was a higher frequency than we'd had before on a conically-scanning imager. And one of the things it lets you do is observe polarization as well as just the brightness temperature itself. And one of the things we looked at early on was these polarization differences. And on the left is the 89 gigahertz. This is from Hurricane Arthur, one of the first hurricanes that was observed by GPM in 2014. And we noticed right away that we'd always seen this signature over water, that the idea is that over water, the polarization goes away into precipitation. It's something that is reduced by a thicker atmosphere, whether that thickness is caused by clouds or rain or ice in the atmosphere. And you can see that pretty clearly here at this towards the center of the storm, you lose that signal and it becomes a low polarization scene. But we found actually the opposite at 166 gigahertz. Because of the water vapor absorption, you don't see the land-ocean contrast anymore. The atmosphere is opaque enough that, especially in the summertime humidity profile, you don't really have any sensitivity to the surface. But we did see these polarizations in the clouds, and they were pretty much ubiquitous everywhere, especially in stratiform precipitation. We notice it's about a 5, 10, 15 Kelvin difference between the V and the H channel, and it seems to be associated with rain, particularly stratiform rain. So we wanted to know, is this a useful piece of signal, or is it just redundant? Is it just pretty much correlated to the brightness temperature itself? And Jia Gong and some other people were able to analyze the data and produce these sort of plots where if you plotted your V minus H difference as a function of the vertically polarized brightness temperature, you got this this nice almost Gaussian or sine wave relationship. There's a clear maximum right around a 200 Kelvin brightness temperature, and at the warmer brightness temperatures, we didn't observe much polarization, and at the very coldest brightness temperatures and kind of the deepest convection, we didn't observe very much either. But something about that mid-range was producing a lot of it, but not necessarily all the time. You can see there's quite a bit of spread. There's some scenes where you had this 200 Kelvin-ish brightness temperature and a lot of polarization, and some where there's not very much. So we looked at that more closely with the radar profiles and found that in the high polarization scenes, there was a very clear bright band, very clear increase, strong slope of the reflectivity from cloud top to the bright band. You can think of that as an aggregate, representing an aggregation process. And it showed up in the dual frequency ratio as well, this very sharp, distinct bright band signature. When you looked at the low polarization scenes, it was much more of a convective looking profile. So the echotops tended to be much taller and much less of a bright band signature, more of just a step function from the snow to the liquid phase. And this is again for the same overall, vertically polarized brightness temperature. So it should roughly be an apples to apples comparison in terms of the total ice water path of the storm. It's just being distributed very differently. And so there seemed to be something about the microphysics and the dynamics of the storm that was affecting the polarization. And so we wanted to understand why that was the case. And some of the largest polarization differences that we noticed occurred in these landfalling or extratropical transitioning tropical cyclones. And when we looked at the characteristics of those profiles, again, very high polarization difference. The echotops, were not necessarily very high. They definitely reached well above the melting layer, but they weren't, these deep convective towers, or these 8 to 10 kilometer echotops. And so I'm working with Rob Schramm, who's a NASA postdoc at Goddard, and he has a background in polarimetric radar meteorology. Has been absolutely fantastic for looking into some of these processes. And he found, when he looked at some of the next-red radars, to look at what was going on in these high polarization cases, well, there was a strong bright band, that strong gradient in reflectivity above the bright band. So it's, again, indicating aggregation. The differential reflectivity, that's a ZDR. So that's a measure of the aspect ratio, you can think of it, of the larger particles, of the ice particles. And that tended to peak. It tended to be positive by a few dB, and it tended to peak around 6 to 8 kilometers before decreasing again towards the melting layer, and then it increases again in the melting layer. So you can think, as you're getting aggregates, they're becoming more strongly oriented, and then as you get the really big aggregates, they start to become more randomly oriented and tumbling. And then once they start melting, that produces another maximum in the differential reflectivity. There's also this measure of specific differential phase that comes from the radars, and that's again related to the aspect ratio of the particles, but it's weighted more towards the lower moments of the distribution. So it's more of an ice water content weighted. So it's telling you something about the aspect ratio of the mid-sized particles. And this also shows that peak between 6 and 8 kilometers associated with maybe some of the smaller aggregates before they get too large and start tumbling randomly. And there's also this cross-polar correlation coefficient, which essentially tells you something about the mixture of particles, and that tends to be lower in the melting layer. So just another sign of kind of a typical stratiform profile. So this kind of confirms that we saw that there's, it's something about the stratiform process in particular that leads to these polarizations. But we wanted to still learn more. So in order to do that, we needed to be able to simulate these observations in a radiative transfer model. And that requires some advances that have taken place over the past few decades in being able to simulate the scattering properties of ice particles in particular. So this diagram is just a schematic of how these scattering property databases have evolved over time and kind of where they rank in terms of computational cost. So this is just a schematic diagram, but the simplest approximation is just using the spherical ice of varying densities. This is very widely used both in precipitation retrievals, particularly from microwave radiometers, and even for data assimilation of some of the first experiments with all sky radiance assimilation use these approximations. Very widely used. It's only recently, I think, start to become being phased out by some of these more advanced methods. And among those more advanced methods are, you can get, kind of the basic oriented particles came from the Mashenko and Travis T matrix, which is really an extended boundary condition method of calculating the T matrix, and that provided a way to get the scattering properties of rotationally symmetric particles. So you could approximate a snowflake as one of these flat spheroids, or you can do oblate or prolate spheroids to sort of approximate plates and columns. So the simple shapes, relatively simple shapes. But to first order, they were able to give you some polarization information, and they're using the polarimetric radar community as well. There's another way to calculate the T matrix called the invariant embedding T matrix. Ping Yang has done a lot of work in this area. I have some colleagues at Goddard that have developed their own code for it as well, and that lets you do some geometries where the EBCM method of calculating the T matrix doesn't converge. So it's also pretty useful. It's a little more expensive, but it does give you a little more flexibility. There's also the computational basis function methods. That's a fairly new idea that lets you do arbitrarily shaped particles. That's very efficient, but so far we haven't really had some large databases that have come out with it. And so at the bottom I put, because even though it's been around for a while, it's the most computationally expensive is the discrete dipole approximation. And there's a couple of codes out there. There's the ADDA and DD-SCAT that have both been used. And this really became popularized by Guosheng Liu in 2008 when he published a database of ice crystal scattering properties that's been very widely used, and it's still, I think, probably one of the most widely used databases. And it's had applications in retrievals and NWP, and proved to be pretty versatile. But even since then, there have been a lot of other investigators that have taken it further. Close and Close, one of my colleagues at NASA Goddard and ESSEC developed a database of thousands of single crystals and aggregates to really improve the GPM algorithms. UC Leonin did the same thing. We used the physics models to rhyme the snowflakes. And so we have one of the big findings of that work was how the radar reflectivity signatures changed once you started adding some rhyming to the snowflakes. And most recently, and something I'm going to really highlight here, is Manfred Freddie Brath and the ARTS group in Sweden developed a database of horizontally aligned snowflakes and their scattering properties. And so for the first, now we have kind of the best of both worlds. We have the realistic properties of the DDA, and we have the orientation from the T-matrix method. So this slide just shows you some of Kuo's particles. So these are randomly oriented large aggregates. And the main point I'm showing this is just to illustrate that at the low frequencies, the Mie approximation held pretty well, especially if you kind of tune the density. You can see that the extinction efficiency, asymmetry parameter, and backscatter all align pretty well with what the Mie theory calculates. But at the higher frequencies, it starts to break apart. You'll find that the best match density might be different than the best match at the lower frequencies, or none of them fit, especially once you get to 165 gigahertz and even beyond there. So really, these DD-SCAT methods are quite essential for doing these calculations. So now we have these observations from GPM, and we have these improving model capabilities. Can we use them to explain the observations that we have? So what you need to do is take those scattering properties and put them in a radiative transfer model that can handle polarization and see if we get something that looks like what we're seeing from GMI. So again, I took that ARTS-oriented particle database, and this is an open access database. The URL is up here. This presentation is being recorded, so you can copy it down and go look for yourself. But it's very useful. And really what they have are this kind of simple hexagonal plate and an aggregate of those plates that have both provided the orientation or the oriented particle calculations for. And there's also a Graupel particle. There's several Graupel particles. Actually, this is the one that we're working with that sort of represents a rhymed particle with random orientation. And then we took a model simulation of an MCS that had a lot of ice in it, and just took us a kind of a profile that had some mixture of all these different types of particles to see what sort of radiative transfer signatures we'd get out of it. And just to illustrate the channels that we're simulating, we're taking the kind of the classic sounding channels near 183 gigahertz, and so that's ±7, ±3, and ±1. And we've also done this, taking this idea to extend it to sub-millimeter by matching the weighting functions at 325 gigahertz. So there's actually 3 channels at 325 that have a very similar weighting function in the atmosphere, and even there's a window at 664 gigahertz that also matches that. So we're using these to sort of evaluate how much you can use sub-millimeter measurements to further quantify these ice properties. And of course, it's not just enough to have the oriented particle database. You need to know something about how those orientations are distributed. So in the database, there's actually a scattering calculation that's done for every beta angle here. So you can think of that as just the tilt of the major axis with respect to the horizontal, and it's averaged azimuthally. So you just think of it spinning around that axis. And then for each of those beta angles, we come up with what the distribution function is, and we settle on using this von Mises distribution, which is just a Gaussian over a circle. And you can see here the beta angle and how it's distributed for the aggregates and the plates. And the plates are symmetric, of course, in the vertical dimensions. So there's we can just flip them in that way, so you only need to go out to 90 degrees. Okay, and so after all that, we ran this radiative transfer model with different orientation distributions for the aggregates and the plates of representing the snow and the cloud ice in the model. And so these plots are just each of those, each column is just one of those frequencies I showed. So if you just focus on the left column, that's the 170 gigahertz, so very similar to GMI 166. On the top is just the I component of the Stokes vector, so that's just the average of the vertical and horizontal brightness temperature. And the top is that nadir, where of course they're the same, and then below that 60 degrees, so that's kind of a very high incidence angle that you would get from a cross-track sounder. And you can see that those brightness temperatures depend pretty much only on the orientation of the aggregates. So there's sensitivity as you get more strongly aligned aggregates, the brightness temperature decreases a little bit, especially at nadir, not so much off nadir. And then the Q element, that's the difference between the V and H. That's the polarization difference that we're really interested in. And that, as you might expect, increases as you get stronger orientation, as that kappa increases and your standard deviation of the beta angle decreases. But it only is sensitive to that orientation of the aggregates. There's really no sensitive to the orientation of the cloud ice. Now, as you go higher in frequency, when we go to 325 gigahertz, now you start to see some sensitivity to both species. And at 640 gigahertz, in that high frequency window, you're much more sensitive to the cloud ice. So this is actually a nice argument for why we need sub-millimeter remote sensing and some of the benefits of that if you have polarization in those channels. But going back to the original question, can we reproduce what GMI is seeing? And so we took that same simulation, we just, which was a large domain MCS, and simulated a whole GMI scan pattern over it. So a few thousand GMI footprints, and tried to recreate that brightness temperature versus polarization curve. And in the background, you have what the observational database suggests, and then each of these lines is one of those different experiments with differently oriented cloud ice and aggregate snow particles. And at 89 gigahertz, it seems like we're not quite able to produce as strong polarization as we see, although some of the more strongly oriented simulations did get close. But at 166, we're actually doing pretty well if you assume a kappa of 4 or higher, and that corresponds to a canting angle standard deviation of around 20 degrees or less. Okay, so aside from kind of validating this model, why is this important? Well, I'd argue that actually has some pretty strong implications for remote sensing from passive microwave databases like you have with GPROF and the GPM constellation. And what I'm showing here is when you take those particles and you assume a random orientation, or kind of what that best fit was with the preferred orientation, is there a difference in the brightness temperatures that you get in the database? And at the vertical polarization at 89 gigahertz, there's pretty much no difference. It's just noise. But once you look at the horizontal polarization at 89 gigahertz, you start to see some biases, and it could be as much as 10 Kelvin lower when you have the preferred orientation. And at 166, it comes out strongly as well. Again, not so much of an effect at 166, but I think I'd argue that it's not negligible anymore. There is still a cold bias when you introduce these preferred orientations, and especially in the horizontal orientation, you introduce quite a strong difference in the brightness temperature. So if you're using randomly oriented particles to simulate another sensor based on the GMI observations, you might not be able to match both the V and the H very well, or especially if it's a horizontally polarized channel, there could be pretty significant bias in that database. So I think it's something that process should be aware of and include as these particle models get more refined. And it's important for a radar as well. So again, I'm thinking from the airborne or spaceborne perspective of looking down at a nadir look profile. Again, if you just look at the difference in reflectivity between the same particle, if it's in a random orientation or if it's in one of these preferred orientations, you can have up to 3 dB bias in the reflectivity, and that of course affects all the retrieval algorithms that come out of that. And and the biases are different at different frequencies. So it's different at Ku, Ka, and W. The maximum kind of shifts towards smaller particles as you go higher in wavelength. And that affects your dual frequency ratio and how you interpret that as well. So that has a whole host of implications for what we're doing with the GPM retrievals and CloudSat retrievals, not to mention anything that might be up there in the future. So we've looked at these models, run through the radiative transfer, and I think that we can explain some of the observations we're seeing, but they're under constraint. We don't have enough information to tell us about the cloud ice from GMI, and there's certainly some crosstalk between particle size and orientation, distribution, and aspect ratio that we need to resolve. So how do we take the next step? Well, we investigate it with some of the GPM ground validation measurements, in particular that D3R radar and ground instrumentation, this Precipitation Imaging Package. And one of the best sources for snow measurements from GPM ground validation actually came recently in the ICE-POP 2018 field experiment in South Korea that was held in conjunction with the Winter Olympics. Even though there was no airborne data, we had quite a bit of good ground data. And the D3R, this is a NASA radar that was built as part of GPM ground validation. It has a Ku and Ka band, the same frequencies as GPM's dual frequency precipitation radar, but it's also polarimetric and has Doppler capabilities as well. And it's all portable. It's basically fits on the back of a truck. You can see it here. So it was able to be shipped out to South Korea and lifted up to the rooftop there and make the observations during that winter field campaign. So it made 5 months of observations. And the scan strategy was such that a lot of these scans were done along radials, which had a lot of good ground instrumentation, such as distrometers. There were a series of vertically pointing radar, MRR radars, as well as this PIP instrument. And it captured many snow events. And I'm not going to read through this list, but just to give you an idea, there were a couple of dozen of snow events that were captured, in particular late toward the end of the experiment. So actually after the Olympics, but between the Olympics and the Paralympic Games, were 3 major snowstorms that we've been looking at quite carefully, because those were probably some of the most fascinating data that were collected from this field campaign. So together with Rob Strom, who I mentioned is my MPP, and Chip Helms and Ali Tokay at Goddard, we're developing a snow retrieval algorithm for the D3R using those same particle databases that I illustrated earlier. So we can take advantage of the oriented particles. And this, of course, will help us identify those microphysical processes and hopefully improve the ice phase parameterization and GPM algorithms. So the whole basis of this algorithm is generating these lookup tables from these particles. And we ran through quite a bit of ways to distribute them, and information in these tables. So they're generated at multiple frequencies and temperatures. You need to be able to account for all the different look angles of the radar, and the size distribution of the ice particles is allowed to vary in both the DMs, that's the mean mass weighted diameter, and the mu, which is the shape parameter, sort of specifies the width of the distribution, and that canting angle distribution that I mentioned. So there's kind of these 3 physical dimensions to the tables that we're trying to find the best fit for. And we include all the radar parameters, so that's vertical and horizontally polarized reflectivity, the extinction parameter, the differential phase, and we're even able to capture some of the correlation coefficients. So that all those things that the dual pol radar measures. So just to give you some sense of these tables, and you collapse them down to just a few dimensions, this is that dual frequency ratio. So this is the difference between Ku and Ka band. And it's been sort of well known, and really the impetus for putting this on GPM was that this tells you something about the particle size, but the relationship between particle size and the DFR depends on the particle itself. And you can see there's different curves for the aggregate particles, the pristine hexagonal plates, and the rime particles. And so the dual frequency ratio alone is not enough to tell you about which type of particle it is. And so that's where the dual polarization information comes in. And so you can see here, on the top on the left are the aggregates, and this is the differential reflectivity. So as the aggregates are small, they have high differential reflectivity, but as they grow, that rapidly goes down to 0. And of course, it depends on that kappa parameter, the orientation distribution. So if you're totally random, even the small particles don't have any CDR, but as you get more strongly aligned, you see that effect. The same is true for the KDP, and that's just weighted more towards the lower moment of the particle size distribution than the CDR is. And for the pristine plates, now you don't have that size dependence. It pretty much only depends on the kappa, because these all have sort of the same aspect ratio, and so and the same is true of the KDP as well. All right, so the idea of the algorithm is to find the best fit of these parameters to the observations, and we have to use a long-array forward model to simulate them while accounting for propagation effects, and that includes attenuation and the differential phase shift. And so from this, we're retrieving a lot of different parameters that are basically the indices to these tables. So it's the size parameter, or the concentration parameter, and W, sort of the ratio of mass between the pristine and the aggregate particles and their sizes, the mu and the kappa functions of their size distributions, and even how much is rhymed in cloud liquid water presence, because that all affects the radar measurements. And from these, you can derive a lot of physical parameters, sort of standard things: ice water content, mean particle size, snowfall rate, and density, using the polarimetric observations. And so I just wanted to illustrate also, we're superimposing the aggregate and pristine particle distributions in sort of a variable way. So you can have two populations that are sort of independent of each other. And this just illustrates, some different ways that those two size distributions could look. And so just again, to illustrate the algorithm mechanics, I just wanted to show one ray of data, and this is taken from an RHI scan. So this is just looking like this is essentially taking a cross section with the radar by starting at zenith and pointing down to horizontal, and the reflectivity profiles on the upper left. So that shows kind of the low reflectivity toward cloud top, and then kind of increasing as you get the aggregation and growth of the ice particles. The differential reflectivity, kind of is pretty low. It increases a little bit and then kind of collapses as you get the big aggregates. The differential phase shift, that's something that's actually something that D3R does a really good job with, because it's proportional to frequency. And so because the D3Rs at KU and KA band, those are much higher frequencies than the S-band radars that we work with in the United States National Weather Service network. And so the phase shift is much stronger. And so that actually tells us a lot more information about the ice water content. And of course, we also see things like the correlation coefficient and Doppler velocity and spectrum width. So a lot of really valuable information that's taken here, and diverse information as well. So looking at that same ray that was highlighted there, this is just showing how the algorithm works. It iteratively fits the observation, so you can see the first guess, and then it fits the ZDR function better. It fits the 5dP trace pretty well by varying all those different parameters. And this is just showing that the model seems to be pretty capable in this case of simulating both the KU and KA measurements and the dual polarimetric measurements. So that provides us some confidence that the models are physically realistic. And you can look at this in terms of Jacobians as well. So that's just how the observation is sensitive to the measurement. And you can see in most cases we have just these diagonal traces that show at a given location the measurement is sensitive to the particle properties there, but not sensitive to the particle properties elsewhere, except when you look at the FDP, because that's the propagation measurement. So anytime you change something in the ice that affects the propagation, it affects all the subsequent measurements along that ray as well. And so you have to be careful to account for that. Now, in optimal estimation, there's this idea of the averaging kernel, which is another measure of sensitivity to observations, a measure of information content. And so you can basically say where this is high, you're getting good sensitivity, and you can be confident in your ability to retrieve that parameter. And so looking at this with these dual pole measurements, we found that the NW, which again is the overall particle concentration, seemed to have pretty good information content. That ratio of mass between pristine and aggregate particles had good information content, as well as the size between them, the ratio of their sizes, and the rhyming. Some things that were not so well retrieved were the orientation distribution, particularly the aggregates and the shape parameter. And then those are pretty secondary order effects on the element, so it's not too much of a surprise that we didn't seem to have so much information about them. We have to be careful about some crosstalk between the measurements as well. So variation in one could be confused with variation in another. But we found the results look pretty reasonable too when you look at the overall RHI. So this is one case where we had a very high ZDR near cloud top, and the retrieval captured a very high pristine fraction there, and a stronger orientation of those particles. You even saw some layering effects that seemed to correspond to the spectrum width. So where the air was more turbulent, we were getting a lower kappa or kind of more randomly oriented particles than some of the quieter air. We saw some stronger alignment there. So that's something that we found that might be interesting and worth looking at statistically over a larger number of events. Okay, but just to finish things up, I want to show some validation data from this PIP instrument. So this is really just a high-speed camera that has an open field of view and a backdrop that takes images of snowflakes at a very high frame rate, and can be used to measure the particles' size, shape, and fall speed. And then those measurements can be in turn used to derive the snow water equivalent rate and size distribution. And here's the time series of measurements from the March 7th snow event, which is a lighter one, but this is the reflectivity both from the D3R at KU and KA band and simulated at KU band from the PIP. And you can see it traces quite well. So this just gives us some confidence that the PIP was capturing something that looked very similar to what the radar was seeing. And we have first order confidence in its size distribution and snowfall rate measurements. When you look at the snowfall rate that's derived from the radar and the PIP, again, there's pretty good agreement. I ran the radar algorithm using all the observations and then without using the dual frequency ratio just to see what the difference would be. And most of the time, though, when you add the dual frequency ratio, that's what gives you more information about the particle size. And so it should help constrain the snow rate better, but it's also very prone to calibration issues. So if the calibration's off, it can be detrimental. And so we see sometimes when it seems that the retrieval that uses this information does better, and sometimes when it seems to do better without that information. So we need to look into that further, and especially how it relates to the calibration. The other thing I want to highlight is the particle density of retrieval. That was something that you really can't get without having that dual frequency ratio. Certainly we're not capturing all the variation that we see from the PIP, but we do see a lot of the dips and peaks that do seem to align with the PIP observation. So that's also pretty promising that we're getting some good information there. So we have made these measurements, and we think that now we can understand a little more about these particles more than we can get just from the satellite data. And so this leads us to formulate new observing systems that could measure these properties. So I already kind of alluded to this by looking at those high frequency submillimeter measurements. But another way you can look at it is also by improving the capabilities of the instruments we already have. And so NASA has this airborne radiometer that was used for GPM validation called CoSMIR, and that has the 166 gigahertz channel with polarization, just like GMI does. But you can configure the scan pattern. So one of the ideas we had was we could fly it and measure in kind of the along track direction. So you're looking at the same profile, but from different angles. And so that can give you the angular dependence of the polarization information. And so we use this for the first time over this past winter in the impacts field campaign. And we have these measurements now that we've taken, and we can see if they agree with the predictions from these scattering models. And this is one case that we collected where we had it coinciding with GMI just to illustrate some of the capabilities of this new scan pattern, and also that you just get much better resolution from the airborne instrument than you do from the satellite, since it's much closer to the area of interest. And so some of our preliminary analysis is showing pretty good agreement with what we expected. We see the I versus Q relationship is quite variable from CoSMIR, especially in this frontal system, which had some embedded convection, so that had that reduction in polarization, but also had some stratiform, which had the strong polarization. We also noted in some of these winter storms in the Midwest, especially some of the shallower ones, that there's a lot of supercooled liquid, which reduces the polarization. So it doesn't necessarily have to be a convective system. It just needs to have some liquid near cloud top, and that can reduce the polarization as well. So something else we found. And of course, I alluded to the sub-millimeter channels. I think that's going to be a big part of our ice measurements moving forward. So at NASA, we're rebuilding the CoSMIR radiometer. So that's actually been in flight before, but one of the things we're doing is changing all of its channels to dual polarization, so we can look at those cloud top signatures and profiles and see how the polarization depends on altitude a little more finely, to learn more about the cloud ice and aggregates. And that's been funded by the ESTO AITT program. We'll have test flights next year, and we'll fly in impacts in 2022. There's also the ice cloud imager. That's going to be the first satellite sub-millimeter radiometer that's in a conical scan configuration. And it'll be on the EU METSAT MEDOP second generation. And I just checked, the first launch is now slated for no earlier than 2024. So we'll still have to wait a few years for that. But it'll have 11 channels going up to 664 gigahertz. And 2 of those will have dual polarization. So that's going to be really helpful, I think, in sort of putting these measurements in a global context. And then on the NASA side, I'm currently working on the study team to formulate the aerosol, cloud, convection, and precipitation measurement. And that's currently under consideration for late 2020s, early 2030s. The idea there is to have multi-frequency Doppler radar, at least Doppler in at least one of the frequencies, and all the passive microwave stuff is going to include sub-millimeter radiometer, just out of size consideration. But that could also be very valuable for matching these measurements with the radar and putting them on a global basis. So that's something that a lot of the details are still being formulated and going back and forth between the study team and headquarters, and they won't make a decision on that until another year or more from now. But currently considering a wider range of orbit configurations, radiometer channel sets, radar, and there's plenty of other instruments too, especially on the aerosol side, looking at LIDARs and polarimeters. So it really should be a nice measurement coming up in about a decade or so. Okay, so that's all I had. I know I worked through a lot of material there, but there's a lot going on in terms of ice measurements from NASA. In a lot of different ways, field campaigns, satellite missions, and ground measurements. But we're learning a lot. These new scattering models, I think, are really going to take us a lot further in terms of being able to understand the polarimetric measurements, and really using them together is the way to move forward with our knowledge of ice and clouds. So thanks for your attention. And I think I have some time for questions.
Thanks, Dr. Munchak. Yeah, if anybody has any questions, they can either type it in the chat or they can raise their virtual hand. You can do that by, there should be a little button with a hand right at the bottom of the attendees panel, or you can send a message to the host saying that you'd like your question to be asked. But we can give them a few minutes.
Okay. Yeah, I don't know if I can see the chat. No, I might have to. Do something else.
Oh, I just got one. How about this? How much does the snowfall detection threshold affect the retrieval of light snowfall?
So, of course, light snowfall is a big challenge with our current instruments, especially for the spaceborne measurements. What we found in a study in 2019, so Gail Scaprone-Jackson led this paper, I think it's in JAMC. I was a co-author as well as Lisa Milani. And we looked at the detection threshold from the spaceborne radars, so GPM, DPR, and CloudSat. And we found that it's well known that GPM misses a lot of the light snowfall, and I forget the exact percentage, but it was something like 90% of occurrence, but on the order of maybe 40% of events that I think it was of actual snowfall volume that it was capturing. So even with the detection threshold of about 13 or 14 dBz, you're missing about half the volume of snow that falls. So it's pretty critical to have a a more sensitive radar from a radar perspective. Now, the other thing we've found is that under some circumstances, GMI, especially at 166 gigahertz, can be more sensitive than DPR in detecting precipitation that has an ice phase. So, exactly how much more sensitive, I think, is still, depends on the database and the algorithm. It's kind of hard to compare those two, but that has some promise. But I think, from the passive microwave perspective, you need to get to those higher frequency channels. From my own work that we're doing with CoSMIR and ACCP, it seems like 240 gigahertz or around 310 gigahertz is sort of the sweet spot for snow, and sort of maximizing the scattering signal, but still being sensitive enough to the full column that you're not starting to lose a lot of the atmosphere to water vapor. I hope that answered the question.
I do have another question from Edward Strobach. I'll read his. Have you looked at time differences in your fitting algorithm to get a sense of why the distribution may change and what processes are responsible for the change in distribution? And they said that they can try to elaborate if their question seems obscure.
Yeah, so with the D3R measurements, we're actually the measurement strategy there was to take these RHI profiles over the sites every 5 or 6 minutes, and so we do have a time series of measurements. And one thing we can see is actually the process of snow falling from the top of the cloud to the bottom. And so a lot of times you'll have these small scale generating cells at cloud top, and those kind of create the initial high concentration plumes of ice crystals that then grow, and they fall into maybe the larger scale cloud, and they spread out pretty quickly, but you do see the evolution of the process there. Now, the problem with this RHI scan strategy is you're only taking one slice, and so if there's any advection kind of perpendicular to that plane, you miss it. So you have to be careful to look at events where the wind or the flow is mostly along that plane that you're looking at. But we do see it, and that's something we're hoping to investigate further when we do the validation with the vertically pointing radar, the MRR that was at these sites. Does that answer the question?
I'm sure they'll respond. And let us know. Here's another. They say yes. Thank you.
Okay.
Which frequency is better for snowfall retrieval, 170 or 600 gigahertz?
Yeah, so when you're at in that 600 plus gigahertz window, that if I can go back, I'd shown the weighting functions. So that window is pretty high in the atmosphere. So unless you're talking about a very dry atmosphere in the Arctic, so that if you look on the left here is the weighting function. So that I think this is for the mid-latitude convection. So it's going to be high. The weighting function will be lower in the winter, but it's still it's sort of the highest of these channels. It's very similar to like a 183 plus minus 1 or 1.5 gigahertz. So I think you're a little bit too high to see snowfall there, even though it is very sensitive to the scattering. So I would say that the 166 or 170 is going to be better for the majority of snow.
Great, thank you. Any other questions? That's it for my queue. But if anybody has any last minute questions, they can raise their hand or paste it in the chat. Okay, in that case, I think we are good to wrap up. Thank you so much, Dr. Munchak, for this great talk. Oh yeah, we're getting thank yous in the chat as well.
Okay, thank you.
Yeah, and then everyone can just make sure to tune in next week. Our seminar series continues.